Welcome everyone. In this video I'm going to show you how to set up the ADS1256 AD converter. We will use an Arduino Nano to connect the circuit board with the computer, and to demonstrate some capabilities of this circuit I built a small voltage divider or resistor ladder, and I will connect the terminals of this circuit to this ladder and measure the voltages. So it's nothing fancy. I will show some pictures later about the circuit, and I will show you all the connections, but the main goal of this video is to go through the registers and show you how to set up everything, so you will be able to control all the parameters of this circuit. For example, the sampling rate, the internal amplifier or gain settings, or you can set up the type of the inputs if you want to use it as a single-ended measurement device, or you want to use it in differential mode, and so on and so on. So what you can see on the screen right now is the map of the registers. So you can see that we have 11 registers. Each of these registers have names, addresses, and values. Each register holds 8 bits, as you can see, so bit 0 to bit 7, and from our perspective there are only 4 registers which are important or interesting, and that is basically the first 4 here. So status, mux or multiplexer, ADCON or analog digital converter, and D-rate or data rate. So now I will go through all of these 4 registers, and I will show you how to read the values, how to write the values, and what the values mean. So now let's take a look on the status register. So this is the status register, and each bit has its description down here. So I call them first 4, but basically the last 4, but we read from the last, because we read from the last towards the first place. So basically the bit 7, bit 7, bit 6, bit 5 and bit 4 is they have a default value, so we don't care about them, and then we can set up the bit 0, bit 1, bit 2 and bit 3. And then this is what is the data output order. Here you can see what you will use, MSB or LSB setup, and then you can enable or disable the automatic calibration. Here you can enable or disable the analog input buffer, and finally you have the data ready, but you have to notice that here is a negation there. So here we don't really do anything. We can maybe change the value of the automatic calibration. So you have the self-calibration at each step, but it's not important, and all the other things are not so important from a beginner's perspective. So the next register is the mux or multiplexer register. So this is the register number 1. You can see it, the address here, and you can see that there are basically 2 groups. So this is the first group, which is the positive input channel, and then you have the group, let's call it B, or the negative channel. And now you can have 2 options. So you can see that you can define all these legs as positive, and here also you can define all of these as negative. So when you set up the value in your code, you will have to send a number to the register, which happens to the ADS.setRegisterValue function. So I just write it down. So ADS.setRegisterValue, and then here we set up the multiplexer, so max, and B, and then we have 8 digits. So this is how we send, and then we have to set up the value here. So B, and then we have the 8 digits, right? And basically they are like divided to 2 groups. So one group is basically from 7 to 4, and one group is from 3 to 0. So for example, let's say that we write this 0 0, let's make it all 0, and then the last 4 is 1 0 0 0. So what we see here is that the AEN0, so this guy here is this, and then here the 1 0 0 0 is this here, so this is the AIN com. So this is basically that we have this as the positive pin and the common is the negative, so this is a single-ended measurement mode. So this is when you use the 8 channels, and among the 8 channels you chose the AIN0 as the positive and the common pin as the negative. So this is simple, and you can do or define a differential as well. So when you send another value, so you choose again the AIN0 as the positive, so, and this is the positive, but now we want to choose another, like from the positive side, and then that should be the AIN1, right? And the code for that is this here, so 0 0 0 1. So this means that this will be the negative, and in this case we use the circuit in differential mode. This will cause a better precision, so it's much better, and you have less noise. So, but you have only 4 channels. And so on and so on. So first, when you define your things here, you can actually choose the positive side, and you can choose the negative side, and that's all. And in principle, this is already done in the ADS1256.h header file. So for example, if you see this part which I selected, then you can see that each of these pins have their name, and then each of these pins are also defined by their binary equivalent codes or numbers. So you don't necessarily have to do the numbers, you just have to define this, but it's much safer with the numbers. So now we have this, we know everything with the multiplexers, and this means that we can jump to the next register. And the next register is the AD converter register, so 8 bits again. The 7, so the first here is always 0, so we are done with that. 6 and 5, we don't care about this, so we keep it 0 and 0, both of these, because we don't want to use this. This is only important if you want to synchronize this AD converter with some external device. So we just don't bother with this. Then we have the 4 to 2 bits, and we also don't bother with these, so these are 0 and 0 again. And then here 2 to 0 bits, so the last or first 3, whatever. This is the PGA, so the internal amplifier or gain amplifier of this thing. And it's very important, because if you want to use it for a lower voltage, so for example, instead of the reference voltage 5 volt, you want to only use it on 0.5 volt, then you also want to be able to use your 24 bits within that small voltage value, and you don't want to lose the resolution that much. So you will use the gain amplifier, and therefore you can keep the precision. So here is just how you define the values. So if you keep it 0, 0, 0, then the input voltage can be like plus minus 5 volt, and then if your reference voltage is 5 volt. So this is basically, the PGA is always defining your range, let's say. So the range, which is in volts, is like the Vref divided by the PGA in principle. So this is basically that if the reference voltage is 5 volts, then the range is plus minus 5 volts. And then if the PGA is increased, so you have the PGA set to 2, then the range is 2.5, and then if it's on 4, then it's 1.25, and then plus minus 0.625, and so on and so on. So you can go down to quite small voltages, and here you will start to see the importance of this, because if you have a voltage which is close to 5 volt and you want to measure that, then if you use the 24 bits and then you have the minus 5 volt and plus 5 volt, you want to divide this scale into 2 to 24 equal parts. But then if you have let's say 2 volts, what you want to measure, then it would be nicer to use a smaller or higher PGA setting. So you measure between minus and plus 2.5 volt and divide it to 2 to the 24 equal parts, because otherwise if you have this previous scale up here and you have your voltage somewhere here, then you don't really use this domain, but you still divide the whole scale. But then if you have a smaller voltage, which is 2 volts, then that is somewhere let's say here on the scale, so you use you don't use this 0.5 voltage, but here you lose 3 volts division. So it's really important. It's like when you are using a multimeter and you try to measure the resistance of something precisely, then let's say if you have a very low value resistor, let's say 1 ohm, you are not trying to measure it in 1 mega ohm range, because you won't have the value precisely. And here the principle is something like that. So if you know your voltage and you know that you don't or will not pass that voltage during your measurement, then you should always follow it with the PGA setting. And the lower the voltage, the higher the PGA number, as you can see, so you can have a precise measurement. So the next register is the D rate or data rate. This is the fourth register, fourth because we start from 0. So you can say this is very straightforward. So based on the 8 bits, you can define several different data rates. And the SPS means sample per second. So if you want to use the maximum speed, then you have this 11110000 value, and then you have the 30,000 samples per second. So this is the maximum value that you can reach, or this is the capability of the circuit. And then you increase the value here, or change the value here, and then you decrease the SPS, and you see that you always divide it by 2. So basically each part is, you basically apply a filter, and then you always get the half of the previous value. So this is this doesn't require any explanation. You just select your speed, what you want to use, and provide the number, and that's all. So we saw that we have 4 different registers that we will use, and we saw also that they require an 8-bit binary number, and by defining this number we can set up the AD converter to our requirements. So let's see what are these numbers, and let's see how to read and write this. So in my source code, which is introduced in the previous video, and also it is in the description of this video, you can see that you can read or write the registers, but in the Arduino terminal we are sending and receiving decimal numbers, because yeah, this is a ASCII terminal, so we have to deal with decimals. So what we have to do when we read the numbers from the registers, then we are reading in the following way. So let's say reading. So when we are reading, we send the letter R through the terminal, and we write a number. So for example, if we write R1 and we send it, that means that we are reading the MUX max register, and we will get back a number. So here you can see a table, and I did it. I did this reading for all the 11 different registers, and for my mux I got back 8 as a decimal number. So for my setup, this was the number that I got, and in binary, so you can see it here, it is this one's 4 zeros and then 1 0 0 0. And if you go back in the video or open the data sheet, you can see what this means. But here we don't have anything that we need to know. It's just if you want to read your register, then you send the R together with the number of the register, which you can see here, and that's all. and if you want to know what is the binary equivalent, then you have to convert it in Excel or something. Yeah, the Excel has a function which can convert the decimal to binary or the binary to decimal, so it's very easy, or you can find several websites on the internet. And when you want to send something, I show you a strategy. So first of all, you want to look up the datasheet, and then you have to copy or assemble the 8-digit number. So if you want to copy, so for example here, you can select, for example, the max again, and then you want to use differential reading using the AIN4 and AIN5. So let's say this. You have to look up the datasheet, and you will see that this corresponds to the following sequence of number. And then you have to convert this to decimal, which is 69. So you have to send this number. So when you write, then you write, and then you write the first register because you want to change something with the multiplexer, and you saw it that the register number is 1, and then you put a space here, and then you enter 69 and then send it. So this is very simple. Or you want to change the data rate. This is also very simple. Let's say we want to use the default value. So let's it is this one. Again, you see what's the value of this, and this is 240. So what you do here is you want to change the data rate. So this is the third register, so W3. You put a space, you just hit space, and 240, and then send it. And you will have the register here set up to the required value. So I show you this in the terminal as well. So here is our terminal. So first let's read the first multiplexer, so R1, and I got the 8. And then let's read the 3, register number 3, and this is 99. So you can see that this is the same as the table. And if I want to write it, I write it and I got it back. So R3, we read it again, and we have at 240. So this was the reading and writing part. And now I show you a circuit, and I show you some things about this setup. So in this video I'm using a different board. So this is a green colored board, and it has the pins and the parts a bit differently as compared to the blue one. There is a blue one as well among the popular versions of this board, but everything is the same, so you don't have to worry. So you can see the pins here. So this row here, it's not so visible, but this is the ground pin basically. So this A in COM, this is basically the common. And if you use in the following way, like you choose the A in I, where I goes 0 to 7, plus you use the A in COM, then you will be able to use 8 channels. And then, so for example, you choose this pin and this pin, this pin and this pin, this pin and this pin, and so on and so on, and you have 8 channels. But if you use in the following way, so you use A in I, plus A in I plus 1, then you have 4 channels, and you always have to follow this. So if you choose this as the positive, the 0, then this will be the negative. Or if you flip the polarity with your circuit, it's not a problem because you will get negative voltage. Or if you choose this as the positive, you have to use this as a negative, and so on and so on. And therefore you will get 1, 2, 3 and 4 channels. So this is the single-ended mode where you have 8 channels, and then this is the differential. So now you want to go here and connect it to the Arduino. I'm using an Arduino Nano, but if you use a Uno or a Mega, it's the same. So let's see what is the configuration. So the GND, it's GND on both sides. So this is the ADS and this is Arduino. And then on this side you have VCC, and that should be plus 5 volt. So this is the plus 5 volt output of the Arduino. And then NC, this is not connected, so just don't connect it anywhere. And then you have the RST, which is the reset, and that should be the D8. And then you have CS, which is the chip select, and that should be D10. Then you have the RDY, which is the data ready, and that should be D2. And then you have the out, that is the data out, and that should be D12. And then you have the data in, which is D11. And then you have the and this is the clock, SCLK. So this is D13, and this has this power down, and this should be connected to the plus 3.3 volts. And that's all. So you just connect in the following way, and you use the exact same source code as I'm using. I will put it in the description, the source code and the files themselves. So you can just copy paste the files in a new folder and just open the project of the Arduino, so this INO code, and run it. And you should not have any problems if you connect the wires according to these things on the screen and using my code. So this is the ADS1256 as you can see it here. So now let's jump to my circuit. So I did not want to record the video because the details are small. I mean, it doesn't really matter, so I show everything on a picture. So as you can see, I made a resistor ladder here, and then here we have the Arduino Nano, and it's connected to the ADS1256. So what I have here is the following. So this is the circuit. Here we have the connection to the Arduino's 5 volt, which is in reality not really 5 volts. And these are the resistors. Each of these resistors are 1 kilo ohm resistors. Of course, they are not exactly 1 kilo ohm, but we assume that it's very close to that value. And here we will read the values between the ground and the different U terminals. So I have 8 terminals, and the U8 is the same as you can see here, so basically the output voltage of the Arduino. And then if you go down in this direction, so you start to measure between U7 and ground, U6 and ground, and so on and so on, you drop the voltage. And the voltage drop is roughly the same because we are using the same resistor values. So if you want to define the value, then that is basically UI, where I is 1 to 7, sorry, 1 to 8, and then this is basically the UA, which is the output voltage of the Arduino, and then Ri divided by the sum R, and Ri is always the sum of the resistors what you are measuring between. So here you have 5 kilo ohm, here you have 4, and so on and so on. And we have some input voltage, and I made an Excel sheet, and I calculated all these values. So I put it right here. So if we have the numbers, we have the resistance, and we have the voltages. So we start from the top basically. So U8, which is the bottom here, is the output voltage of the Arduino, and then we go down to U7, so we are here, then we measure 4.1, and then so on and so on, and then at the end, so here the U1 is 0.586 watts. And then I also measured this with a multimeter, and this is also or of course the same, because I measured this and put it here, and then I calculated all the others, but then you can see that we get roughly the same values. Of course it will not be the same, because the voltage can change a little bit, and then also the resistors are not exactly 1 kilo ohm values, which is of course can be expected. But what we can do now is we open the terminal and then do a measurement or two to see what is the value. So we have the terminal here, and I just want to measure the 8 channels. So I did it. So the first value here is 4.78, that is like 0.1 away from this, and then we have 4.17, and that is more or less close to this value, and then 3.5, that is also okay, 2.96 again, 2.37, that is also close, 1.78, it's close again, 1.2, and 0.6. So as you can see that this connection, or this kind of circuit which we have here, is perfectly measurable with this kind of setup. You can see that I just have a bunch of cables, everything is connected to the terminals, and it works. So you could see that if I sent the command to the Arduino, then I received the numbers, and they were quite close to these values. So it's really simple. So I hope that this video was helpful for you, and I hope that you will be able to use the source code as well, and you will make this circuit working for you. So see you in the next video.